Okay, so we've done this in chapter 5 where we used our Q equals MCAT, and you're doing the exact same thing in this problem here. So it says calculate the enthalpy change. Enthalpy change, remember, is delta H. Upon converting 1 mole of ice at negative 25 degrees Celsius to steam at 125 degrees Celsius under constant pressure of 1 atmosphere. And they gave you all of the information that we need to know. We need to know the specific heat of ice, of liquid water, and steam. So they gave them to you respectfully. So we have ice is 2.03 joules per gram Kelvin. The specific heat for liquid water is 4.18 joules per gram Kelvin, and steam is 1.84 joules per gram Kelvin. They also gave us the heat of fusion and the heat of vaporization. We'll need that when we need to find the energy during the phase changes. So if we go back and think about our curve, our heating curve, we know and since we're talking about water here, we had segment A to B, here was BC, here was C to D, D to E, and E to F. So we said that at this point was when we had ice. This point, or solid, this point is when we had our liquid, and this is where we had our gas. So when I'm finding these 3 particular segments, I'm going to use Q equals MCAT. Well, we don't know the mass, but they gave us moles, and we also know we could convert that 1 mole of ice into grams by using molar mass. We know C because they gave us all of the specific heats. So when I'm finding ice, or when I'm using the solid, when I'm looking at ice and trying to find Q equals MCAT, I'm going to use the 2.03. When I'm trying to find the Q during the liquid phase, so when I'm trying to find the Q during the liquid phase, I'm going to use C as 4.18. When I'm trying to find the energy for the gas phase, I'm going to use C as 1.84. So let's just do an example of one of the phases. We'll do the solid phase, and then we'll also do one of the examples for the phase change, and then I want you to do all of them and then tell me what your final answer would be once we add them all up and find the total change for enthalpy, or that total energy change. So let's look at one of these. Okay, so let's just do from ice, and we know that we have Q equals MCAT. Okay, so Q equals, I don't have grams, I only have moles. So the first thing I need to do is think about in 1 mole, sorry guys, my handwriting is probably really bad on this, 1 mole, and in 1 mole we know for water, there's 18 grams of water per that 1 mole. So ultimately, I just have 18 grams. But I just wanted to show you that we'd have to use our molar mass. So I had 1 mole of water, but I needed to convert that by using molar mass. So instead of writing all of that, let's just write 18 grams. Because now we know that when we're talking about mass, we need grams, and that was 18, and we found that by using molar mass. Okay, so we have 18 grams, and this is in the solid state. So actually, we're finding this for segment AB. So at segment AB, it's ice, it's solid, and C, the specific heat of ice, is 2.03 joules per gram Kelvin. Now I need to think about temperature change. Temperature change is going to be final minus initial. For segment AB, B is where it's at 0 degrees, and segment A is at a negative 25. So I'm going to take a 0 minus negative 25. So that means my change in temperature was 25 degrees Celsius, which a change in degrees Celsius should ultimately be the same thing in Kelvin. So I can say 25 Kelvin. So if I multiply that across, you'll get an answer. And that will be in, my grams will cancel, my kelvins will cancel. So your answer should be in joules. So whatever we get here for our joules, that's going to be the energy for segment AB. Now, you're going to do the exact same thing for segment C through D and then segment E through F. But I'm going to use a different C value for specific heat for water and steam, and I'm also going to use a different change in temperature. So I think you can do those. But let's do an example of what we would do for a phase change. So for a phase change, we know that the temperature doesn't change. And they also gave us this information in our problem that says for water, the heat of fusion is 6.01 kilojoules per mole. So when we did segment A to B, we actually had our answers in joules. I want us to find our answer in joules. So whenever we find Q for a phase change, we just want to take our heat of fusion, whatever our latent heat is. So Q is going to equal our latent heat times moles, however many moles we have. So in this case, for B to C, that would be where we have our heat of fusion or melting. They gave us our latent heat value as 6.01 kilojoules per mole. I want that in joules. So if I wanted that in joules, I'm going to multiply by 1,000. So I should have 6,010 joules per mole. So that would be my latent heat. Well, how many moles did we start off with in terms of ice or in terms of our water? Well, it told us that we have 1 mole of ice. So how about just 1 mole? If I do this, I'll see that my moles cancel, thus leaving me Q with a unit of joules. That's exactly what I want. So in this case, Q is for BC. This is again for segment BC, is equal to 6,010 joules. Now, you can do the last 3 phases. Once you have all of them, you're going to add them all up, because then that would be the total enthalpy change when we're converting 1 mole of ice at negative 25 degrees Celsius to steam at 125 degrees Celsius. We should like 55,000 joules, or 55 kilojoules if we want to say. So you should be getting something around there. If you don't, then send me an email. We can talk about it. Okay, so critical temperature and pressure. We know that gas can liquefy at some point, and usually that happens when we have some type of pressure that's applied. However, if the temperature is high enough, the liquid phase won't form until the pressure is high. So let's say that critical temperature is the highest temperature at which a distinct liquid phase can form. So it's the highest temperature at which a liquid can exist. So critical temperature is the highest temperature at which a liquid can exist. Critical pressure is the pressure that's required to bring about the liquefaction at this critical temperature. So at a certain temperature, it doesn't matter how much pressure we need to cause a liquid phase to form. No amount of pressure is going to change that back to a gas, back to a liquid. So critical temperature, let's just reiterate, is the highest temperature at which a liquid can exist. And then anything past that, it's going to be no amount of pressure can bring it back to that liquid phase. Now, this is kind of a new area for us that's, I think, more highly researched, so it's kind of a hotter topic right now. It's called a supercritical fluid. We're going to talk more about that when we get into chapter 12 as well. But when the temperature exceeds the critical temperature and the pressure exceeds the critical pressure, then the liquid and the gas phase are actually indistinguishable from one another. And we call this a supercritical fluid. So a supercritical fluid happens when the temperature moves past the critical temperature and then the pressure exceeds critical pressure, and we can't really tell if we have a liquid or if we're talking about gas, it's because it's like picking one from the other, it's indistinguishable. It can have properties of a liquid, it can have properties of a gas. So we call this a supercritical fluid. Now, we've also talked about vapor pressure before, and this is probably one of the last properties of a liquid that we'll talk about before we get into something about liquid crystals. So at any temperature, some molecules in a liquid will have enough energy to break free. So we know that if we continue to apply energy, if we continue to increase the temperature of a liquid, we know that ultimately some of those particles are going to overcome their intermolecular attractions and break away into that gas phase. So as the temperature rises, the fraction of the molecules that have enough energy to break free will increase. So if we're looking specifically at our graph here, number of molecules compared to kinetic energy. Okay, so let's follow our blue trend, so at the lower temperature. So I see here that I have, at a lower kinetic energy, a higher number of molecules. But let's say that I raise the temperature. Let's say that I'm adding energy. Now, what's going to happen to my blue line, instead I'm going to see a shift where I'm going to have a number of molecules that are at a higher kinetic energy. So I'm not going to have as many molecules here at this lower energy, at this lower temperature. Instead, I'm going to have more molecules that are going to be at a higher temperature. I'm going to have more of a distribution. And let's say that this is going to be that energy needed to escape. This is the minimum energy that's needed for those molecules to escape. So I can see in my red, under the area here, for my red graph, my red line, that I have more number of molecules here in terms of the kinetic energy being able to escape. But in the blue, at that lower temperature, we're not going to have as many molecules that are escaping. So I need lots of kinetic energy for those molecules to escape. Okay, so in terms of vapor pressure, as more molecules escape the liquid, the pressure they exert will increase. So remember, we thought about vapor pressure last year, or we talked about it in terms of this dynamic equilibrium. So at any instant, and specifically in this case, we're looking at ethanol. So we're talking about ethanol here. We have liquid ethanol that's in a little chamber here, and then we have just another system, some evacuated flask that has zero pressure. So let's say that we're starting to evacuate some of this liquid ethanol into our evacuated flask here. Ultimately, what's going to happen is the system is going to go through some type of equilibrium. So the molecules are going to leave and enter the liquid at equal rates, and the pressure is going to reach some kind of steady value where the number of particles that are moving from the liquid to the gas phase is equal to the number of the particles that are moving from the gas to the liquid phase. So at any instant, some of the ethanol molecules at the liquid surface will possess sufficient energy to overcome some type of attractive forces, so that means they can escape into the gas phase. At any particular temperature, the movement of molecules from liquid to gas is going to move on continuously. So as the number of gas phase molecules increase, the probability increases that a molecule in the gas is going to strike the liquid surface, and that liquid is going to recapture that molecule to be part of the liquid. So eventually, like we just said, and what the illustration is showing, is that the rate of the liquid turning into the gas will be equal to the rate of the gas turning back into the liquid. So ultimately, the pressure is going to become constant. When this happens, we call this vapor pressure. So the liquid and vapor reach a state of what we would call dynamic equilibrium, meaning that the liquid molecules entering into the gas phase will ultimately even out to where gas particles are going to move back into the liquid phase. That's our dynamic equilibrium. So liquid molecules will evaporate and vapor molecules will condense at the same rate. And that is what we'll call vapor pressure. when vaporization occurs in an open container, we know that the gas molecules spread away from the liquid. So very little is going to be recaptured back by the liquid, and equilibrium can never occur. So this dynamic equilibrium, we really need to think about it usually in a closed system, because if you were just boiling water on a stove, you're boiling water in a pot on the stove, then those gas particles, that water vapor, can just escape out into the rest of your kitchen, and very little of them will go back into that pan or pot of boiling water. So usually we think about this in terms of closed systems. Okay, so the boiling point of a liquid is the temperature at which its vapor pressure will equal atmospheric pressure. The normal boiling point is the temperature at which its vapor pressure is 760 torr, or we know that's equal to 760 millimeters of mercury, or equal to 1 atmosphere. So boiling point, if we just want to give it a definition, again, it's just when my vapor pressure is equal to the pressure that the atmosphere is also exerting on that liquid. They need to be equal to one another. The graph off to the right just gives us an example of vapor pressure versus temperature for several different liquids. Now, vapor pressure, the natural log of vapor pressure of a liquid is inversely proportional to its temperature. So if I look at my graph here, I have my natural log of my vapor pressure here, and that is going to be inversely proportional to temperature. So I have 1 over temperature, or 1 per Kelvin here. There were a couple people that looked at this type of trend. The relationship between vapor pressure and temperature is given by an equation, and that's called the Clausius-Clapeyron equation. That's a thing to say. So it says the relationship is quantified in the Clausius-Clapeyron equation. So in this equation, we see that the natural log of pressure, of my vapor pressure, is equal to a negative delta H. What is that? That's that change in enthalpy. So if I have, and specifically I want that change in enthalpy for vaporization. So that would be my heat of vaporization, where I'm vaporizing, that phase change. So let's go back. My natural log of vapor pressure is equal to that change in enthalpy, specifically at that heat of vaporization, divided by R, which we know is that ideal gas constant, times temperature, plus C. Well, what is C? C is a constant value. And specifically, that C was found by two guys, Clausius, Clapeyron. You'd never guess that. So C being constant, we'll talk more about that in a little bit, but ultimately, probably more in chapter 12, but ultimately what you need to know is that Clausius-Clapeyron is showing a relationship that the natural log of vapor pressure is equal to the inverse of temperature. Now, or is proportional inversely to temperature. So we could say it either way. So Clausius-Clapeyron equation, you will probably see this on your FRQ. I doubt that you'll see a multiple choice question on your AP test about this. You may, like I said, see this on your FRQ, but I'm not sure how much this is actually tested on your AP test. I don't think very much. So we'll come back to this though in chapter 12 again. Okay, so let's just talk about boiling points or freezing points and what they depend on. So we said earlier in the chapter that intermolecular forces are very important in determining a boiling point or melting or freezing point. So the stronger the forces between molecules, the harder it is for separation of those molecules. So then if I have strong intermolecular forces between molecules, that means I'm going to have to add more energy to overcome them. So boiling point or freezing point would increase there. So the stronger forces, higher boiling point or melting point of a substance. But kinetic energy also, remember we said that was the antagonistic kind of force against intermolecular forces. Because if I have greater mass of molecules, then I'm also going to have a greater boiling and freezing point just because the molecules are so massive. It's going to take a lot more to overcome those intramolecular attractions as well. The higher the temperature, the faster the molecules will move. So then the more easily those molecules can break because we can overcome those intramolecular attractions as we add energy, and we can think about that as an increase in temperature. And if we increase temperature, intermolecular attractions become weaker, so then we can get our boiling point or our melting point a little easier. So increasing boiling points and melting points imply increasing heats of vaporization or fusion. So if I have a higher boiling point, if I have a higher melting point, then that means that I have really strong intermolecular attractions. So my heat of vaporization or my heat of fusion should also be high. Okay, the last thing in this chapter that we need to talk about are something called liquid crystals. Now, liquid crystals are a little different in that they're kind of like this intermediate state. So some substances have a hard time going directly from a solid state to a liquid state. Sometimes they want to like fluctuate during that phase change where we see that they can have some properties of a liquid, some properties of a solid. And if that happens, then we call that a liquid crystal. There are a couple different types of liquid crystals. We actually are using liquid crystals a lot in today's society. So specifically, we use them as we've used them as pressure sensors. We can use them as temperature sensors. On liquid crystals are used in our digital watches now. Like you may see the LCD, which is just standing for the fact that it has liquid crystals in it. Laptop computers have liquid crystals in them. So a lot of new technology is utilizing these liquid crystals. The fact that it's this intermediate state between solids and liquids, and they can exhibit traits of both. So because of that, they're very useful to us. They have very weak intermolecular forces, and those intermolecular forces can be affected very easily by changes in temperature, changes in pressure, or some type of electric field. So it's really easy for us to manipulate these crystals to kind of get something that we need. So in terms of our liquid crystals, we can show that there are several different types. We can have the liquid phase, so that's where we know that molecules are arranged more randomly and they're easily able to flow past one another. We could have something called the nematic liquid crystalline phase, and that's where we have all of our molecules in our liquid are all aligned in terms of the long axes. So if I'm looking all of these molecules, so I have all of my molecules aligned in this long way, but their ends aren't really aligned. So they're still more random. They're all aligned in the fact that their axis is the same way, but still they're kind of shifted where they're not still perfectly aligned. So we could have also something called a smectic liquid crystalline phase. We'll call this a smectic A liquid crystalline phase, and that's where the molecules will align in layers. We'll have long axes of molecules that are perpendicular to layer planes. So I'm actually getting like planes of some of these liquid crystals. So I can see that these are more aligned with one another. So I can get like a plane here, and then I can see that I have a plane also down here below. We could also have smectic C liquid crystalline phase, and that would be where the molecules are aligned, but they're at an incline with respect to layer planes. So the only difference between smectic A and smectic C is that smectic C is at some type of incline, and then smectic A is really at no incline at all. And the nematic liquid crystalline phase is where they're starting to line up. So all of those long axes of the molecules are trying to line up, but they're not perfectly aligned like they are here in smectic A or smectic C. So the liquid phase looks much different, where all of them are just arranged randomly. But then we can get our nematic liquid, smectic A, smectic C. So there's some ordering, there's some type of structure in terms of these three liquid crystals. So that's why we can say they kind of exhibit some properties also of a solid. because there is some type of ordering to them, but their intermolecular attractions are not as strong as a solid. So we can still say that they will possess some order in terms of traits in the liquid sense as well. Okay, so the last couple slides, guys, are just talking about the nematic liquid crystalline phase, smectic, and smectic C. So in nematic, again, they're just ordered in one dimension and they're just ordered on that long axis. Their ends are not all aligned. So we still have a little bit of disorder kind of in this. But in smectic liquid crystals, we see that our molecules are starting to layer up. So in smectic A, we see that they're not at an incline at all with respect to a layer. Instead, we have them perpendicular to their layer plane. But in smectic C, we see